Okay, guys. Good morning to all of you.
Good morning, sir.
I hope you have had a very
Good morning, sir.
interesting, enjoyable experience during the Diwali vacations. So now it is time for us to get back on track and start with our studies. All right. So we will continue with whatever we have. We left off with a design example for the negative voltage clamp, if you remember, during the last session. And we'll continue with other types of voltage clamper circuits. Remember what basic job of the voltage clamper is to shift the DC level of the signal. So we are interested in shifting the DC level. There are various different circuits. DC level can be shifted in the positive as well as in the negative direction or polarity. So we start with the negative biased clamper circuit. We have already seen the positive clamper circuit and the negative clamper circuit. Now this is another variety of the clamper circuit. I hope you are able to see the screen. No, OneNote page. Yes.
Yes, sir. Yes, sir.
Okay. All right. So let me start with the circuit itself. So as usual, the circuit consists of a capacitor, a resistor, okay. This is the output. So what is the difference? The difference is here. I'll use a different color so that you'll be able to understand the difference. So here is the difference. Well, otherwise this cathode would have been connected to the ground. Okay, so if you call this, mark this as ground. But now this is connected to a different potential. We call this as VB1. Okay, and let us say it is some positive voltage, something like that. Okay, this is where you will get the output voltage. This is your input. This is your capacitor C1, R1 as usual. This is V1. Okay, so all right, let us have a look at the signal. Your input signal is, we'll again use a sine wave. Again, this is plus 2, this is minus 2. Okay, and now let us have a look at what we get at the output. And then later on find out why it happens. So first of all, the DC level is shifted in the negative direction. That is what you have to first of all understand. And that is equal to that VB1. So this is what happens. You see the DC level is shifted down, right? And this value is VB1 plus VF. So there is a DC shift here for this particular circuit. Okay, let us see why this happens. Of course, it's very simple to understand that way. So output voltage, first of all, output voltage cannot exceed VB1 plus VF. Why is this condition there? First of all, please remember that again this capacitor will be charged to in this particular fashion. And now since we are having this bias also term associated with this, biasing voltage also associated with this, you will not be able to have output voltage which is greater than VB1 plus VF. This is VB1, this is VF. So obviously output voltage cannot exceed that. Capacitor charges to, so the VC, capacitor will charge to E minus VB1 plus VF when input is positive. Understand this? Understand this first. So what is the value across the capacity? Guys?
So you are not clearly audible.
Now am I?
Yes, sir.
Okay. So what is, we started with the value voltage across the capacitors C1. So VC1 will be equal to this E, but at the same time, what is the other end of the device, other voltage at the other end of the capacitor, other terminal of the capacitor? It will be this voltage, which will be equal to VB1 plus VF. You remember this is VF.
Yes, sir.
Voltage across this. So whatever is the maximum voltage will be E minus VB1 plus VF when your input is positive. Okay? Now when the input goes negative, output voltage will be equal to what? Minus of E plus that capacitor voltage VC. See if you can understand this. Initially this was positive, so that is the reason why the capacitor got charged to E. Now I am applying minus E to that. At the same time there is a voltage already across the capacitor. The capacitor was charged to this value VC1, which was E minus VB1 plus VF. Why E minus VB1 plus VF? The reason is that your output voltage cannot exceed VB1 plus VF. Why is the reason that it cannot exceed this voltage? Any reason for that? Because the diode will get forward biased. As soon as the voltage over here tries to exceed VB1 plus VF, the diode will be forward biased and it will be clamped to that particular value. Okay, so output will be clamped to maximum value of VB1 plus VF. We have already seen the biased clippers. In a similar fashion, we have this kind of network. So it should not be a big issue. So then what is the output voltage? We already have evaluated VC. So if you put it in this equation, it becomes minus E plus what is the value of VC? It is this. So you have E minus VB1 plus VF. Look at the number of brackets over there. Of course, I can simplify this to minus E. Let us say if I take out minus sign common, it's minus sign already common. So plus E minus VB1 minus VF. Okay, what does this give me? It is 2 times E plus VB1 plus VF. This is the output voltage. So what you'll have here, this value is 2 times E, of course negative, plus VB1 plus VF. This is the peak value when the input is negative. Okay? So this is your output actually. But is it changing to peak voltage? Let us find out. So output peak to peak. This is VO PP, that is peak to peak value. So what is the output voltage when input is positive? It is this VB1 plus VF, and when the input is negative, the peak value is this. So I simply have to find out VB1 plus VF. This is one value minus 2E plus VB1 plus VF. Okay, what does this turn out to be? This VB1 VF will get cancelled, so it will be 2 times E. So you see that the peak to peak value is still 2 times E, which actually is the value of the input itself. So it is not changing the peak to peak value at all. But what is happening? It is shifting the waveform in the negative direction. That is the reason why it is called as negative clamper first of all, and then why.
So you are not audible.
Guys, please respond.
So you were not audible.
Okay,
There
I
was a
asked whether this particular circuit is understood or not.
yes, sir.
I think it should be fairly simple because we have already seen such a kind of circuits earlier.
Yes, sir.
Okay, so obviously the next circuit is the positive biased clamp. You can call this clamp, voltage clamp, clamper, all those are synonymous terms. So obviously now I can have the circuit like this for the positive clamp. Again your C1, R1. Now look at the diode, the way in which the diode is connected. So this is going to be D1. This is where you apply the input. This is where you get the output. If you look at the waveforms, okay. This is again your input waveform plus E minus E. And now, if you look at the output, now we have an interesting situation here. What do you predict? What will happen? Yes?
So it will be shifted in positive direction,
Very
like
good.
in
It
a
will be shifted
negative.
in positive direction by what amount? So it will be shifted by this much amount, which is actually,
So V1.
yes, very good. Is that the only thing? VB1 minus VF. Remember
VF,
this.
yes.
All right. So you
Yes,
have
sir.
a positive shifting mechanism. Or the signal DC content is shifted by this much amount. Let us just have a look at it. Its operation. D1 is forward biased when input is negative. That is when input is minus E. So start with that. So the voltage VC will be VB1 minus VF plus E, and output voltage is VB1 minus VF. Right. When input goes positive, that is when input is plus E, your output will be again E plus whatever is the voltage across the capacitor. See, the basic operating principle or the heart of this entire circuit depends on what is the voltage across the capacitor. That's all. Because output will be E plus that particular voltage across the capacitor. So this turns out to be E plus VB1 minus VF plus E. That is 2E plus VB1 minus VF. That will be the peak value. This value. CB2E plus VB1 minus VF. Again, you can verify that the output peak to peak value is not changed. It is 2 times E, this output, plus VB1 minus VF. This is the peak value minus VB1 minus VF, which is the other peak, negative peak. So the peak to peak value, if you evaluate VB1, VF, all this gets cancelled, and it again is 2 times E. So output peak to peak value is not changed. Only the DC value is going to be changed. All right, guys.
Yes.
Okay.
Yes, sir.
Yes, sir.
So then we will proceed to another type of clamping circuit, and that is a Zener diode clamping or clamper. Okay. Now it works as very similar to the biased clamping, except for that we don't require external bias. Okay. So if you look at this, it will be very similar to the operation will be exactly same as that of the positive and the negative diode, sorry, the positive and negative bias clamps. So we have a diode here, and interestingly, we have a Zener diode like this. Okay. As per our convention, what we will do is we will use a different color so that the new component is highlighted. So this is going to be VD, sorry, VF, and this is going to be VZ. This is going to be the output. Again, the concept here is that you rely on the breakdown mechanism of the Zener diode. So if I look at the input waveform and the corresponding output waveforms, this is plus E, this is minus E, and if you look at the output, it's going to be something like this. Right? Okay. All right. So the value will be Vz plus Vf. Just replace that Vb, and still you'll see that the output is equal to 2 times E. All right, guys.
Yes, sir.
Okay, let us see how quickly see how this works. It's very simple actually. If you have understood the biased clampers, you will be able to understand this very easily. So when input voltage is positive, what will be the output voltage? Output voltage is Vz plus Vf. Why will it be Vz plus Vf? Guys, why should it be Vz plus Vf? Just let me see if you have understood the biased concept. Because after that,
taken across
this diode will be forward biased. Okay.
Biased,
Output
sir.
will always be Vf plus Vz. Once the Zener diode goes into the breakdown, output is going to be Vz plus Vf only. That's all.
Plus Vf.
Isn't it? So the capacitor C1 will charge to what is the value? On this side it is E, and on this side it is Vf plus Vz.
Plus
So
Vf.
it will be charged to
So you are not audible.
what will be the output voltage now? Input is negative means minus E. What will happen? It will be, I'll take negative sign common, E plus E minus Vz plus Vf. That gives me minus 2 times E plus Vz plus V.
Plus VF.
Right? So
Yes,
this is
sir.
the maximum value, this value. What it be? What is it? 2E plus Vz plus V.
Plus VF.
Okay. And then verify whether the output peak to peak is the same. This is the positive peak minus this entire thing minus 2 times E plus Vz plus Vf. So this is what? So the peak to peak value is still 2 times E.
2E.
Alright. So this is your Zener diode clamper. Of course, it clamps the waveform in the shifts in the negative direction. Similarly, we have the Zener diode clamp for the positive clamping. The only difference is that, okay, we'll see that also. So positive Zener diode clamp. People are still joining. Why these people are so late? Even if at the comfort of your home, if you're not able to make it on time, I don't know. Anyways, so this will be the circuit. The only difference is the orientation of the diodes. That's all. See, both the diodes are. So this is for the diode D1 and for this Zener diode, the polarities will be like this. Okay. So it is going to be exactly the same as that of the biased clamper. Let us see. This is plus E again, minus E. So your output will be something like this. Now look at the way in which it is shifted. This value is minus Vz plus V. Okay. Again, when input is negative, D1 is forward biased. So output voltage start with input negative. Okay. So output voltage is minus Vz plus Va. and capacitor is charged to minus Vz plus Va plus E. When input is positive, D1 is reverse biased, output voltage is E plus voltage across the capacitor. We have already found out the capacitor voltage. So this turns out to be E minus Vz plus Vf plus E. That gives me 2 times E minus Vz plus Vf.
Plus Vf.
Okay, so this is the output voltage when the input is positive. So this value, it is 2E. You can look here, minus Vz plus Vf. Minus Vz plus Vf. Again, verify whether output peak to peak is 2 times E. So one value is this 2E minus Vz plus Vf minus what was the value? Minus of Vz plus Va.
Plus Vf.
So you can see here that this term gets cancelled and it is again 2E. So output voltage, peak to peak voltage is retained. Okay? Is this fine? Any doubts, any questions with this? With that,
No, sir.
with that we have completed the clamping circuits as well. Now only 3 small topics are remaining. That is, immediately we are going to go with the DC voltage multipliers and then astable and monostable multivibrator. Okay, that will be the end of the syllabus for you guys. Right, so maybe 2 or 3 more lectures. You'll have to bear with me. Anyways, so shall we start with DC voltage multipliers? It's going to be very, very interesting. What my plan is to complete the multipliers and then we go for the simulation. As per our practice, I keep on showing you the simulation outputs also as soon as we complete the topic. All right. So we will start with a new topic. Guys, are you there with me?
Yes, sir.
Yes, sir.
Okay. Okay, so very interesting circuit. One more circuit. It comprises a little bit more number of components over here, but very interesting, very easy if you logically look at it. Okay, so let us have a look at the circuit diagram first of all. So you have a capacitor here, you have a diode here, then again you have a diode here, capacitor. This is the circuit for what we call as the voltage doubler. As the name suggests, this will be your load. So this one is C1, this capacitor is C2, this diode is D1, this diode is D2. This is where you will apply an input. Now, first of all, understand one thing, that I am supposed to double the voltage. I mean, as the name suggests, the voltage doubles. Means what? It simply means that whatever is the peak value, suppose this is the peak value E for any input waveform. Doubler means I should have the output voltage getting double of this. So this should be 2 times.
Yes, sir.
In simple plain words.
Sir.
Okay. I'm just showing you a random waveform. Okay. So that is the concept
Yes,
here.
sir.
We are increasing or we are multiplying the peak value. So necessarily your input is AC and output is DC. This is interesting. Your input to this circuit is always going to be AC and is going to be DC. Let us see what happens with the actual waveform. So my input waveform, I will again use a square wave so that it is easier for you to understand. David Bell also follows the same logic. All right. So this is your input waveform. Remember, this is AC. Input is AC. All right. And if you look at the output, interestingly, the output is something of this sort. We'll see what is this, why this is happening. But this value happens to be 2 times E. Let us see how this happens. So have you seen, do you see the input and look at the output? What is the difference? First of all, your input is, guys,
Input is AC.
input is AC, whereas the output is DC.
DC.
This is one very, very important thing that you should understand or remember. All right. What I am trying to do is, many times I require that the output voltage, that is the DC voltage, should be a multiple of the input peak voltage. Most of the times, if I want to go on increasing the peak to peak, rather the peak values, very high voltage DC, if I want to create, I will use such a kind of circuit. Okay. So let us see how this actually works. Okay. So first of all, let us, so voltage doubler produces output voltage DC, which is approximately double the peak voltage of input, which is AC waveform. Okay?
Yes, sir.
Okay, let us understand the working of this in very simple way. Okay, I'll redraw the circuit. So when, always start with the negative half cycle for explanation. Okay, this is very easy. If you start with positive half cycle, it will not work properly. I mean, you may not be able to explain it properly. Okay. So always start with when input voltage is negative. Okay. Now when input voltage is negative, I'll reproduce this diagram again. So if this is your ground and we are talking about negative half cycle, that is when input is negative, what is the status of D1, D2, C1 and C2? So what will happen to D1? If your input is negative, so I'm applying minus E here, what will happen to D1? Whether it will be forward biased or reverse biased? Tell me. Guys? Yes?
D1 will be forward biased.
Speak
D1 will
louder.
be forward.
D1 will be forward biased. Why? But how will E be connected? E is DC. You have a capacitor.
Yes, sir.
So how will that happen? We have already seen this. Always when we start by assuming C1 is not charged.
Yes, it is short circuit.
And when a capacitor is not charged, yes?
So it will act as a short circuit.
Yes, excellent. It will act like a short circuit. So as if this capacitor is not there initially, when it is uncharged for the very first cycle,
So you are not audible.
let us not directly do away with the capacitor, but let us keep it for the time being. The diode is not there. Is forward biased, means it is as good as a short circuit. And I'm applying E over here. This is the ground. So what will be the voltage across the capacitor now? What about the other part, D2? What is the status of D2? What is the status of D2? Whether reverse bias? Agreed. D is forward biased. What about D2? Guys? Yes?
So reverse biased.
Absolutely, it is reverse biased. Why is it reverse biased? Because look at the anode voltage
Anode is connected.
and look at the cathode voltage. Okay? So
Yes, sir.
it will be
Reverse bias.
reverse bias. D2 will be reverse bias. So it is out of picture. In fact, there is no output here. Output is disconnected. As it is disconnected, there is so this capacitor and all those things are even out of picture for the first cycle. So what is the voltage across capacitor now? What will the capacitor be charged to? Please don't forget that the diode has got a forward voltage drop of Vf. Okay? So this is plus, this is minus. So what will be the voltage across the capacitor C1?
E minus P.
Very good. So the voltage across capacitor C1 is going to be E minus Vf.
Yes.
Just remember that the voltage across the capacitor is now E minus Vf. Now, during the positive half cycle, what is going to happen? Okay, let us first of all update the values. Okay, so here we have the diode. Okay, I'll just draw it full for the time being. Then you have another diode here and a capacitor here. Let this be a repetition, but this is very, very essential for understanding. Okay, now during the positive half cycle. So I'm applying plus E now. What is the voltage across the capacitor? It is already E minus Vf. Now I'm applying E like this, plus minus E at the input. So what will be the voltage here at this point, at this node? Yes? Call this node A. So at node A, EA, what will be the voltage? Remember the polarity of the is like this. So what will be voltage at A, point A? Guys?
Positive.
E plus whatever is the voltage across
Plus.
capacitor C1, isn't it?
Yes, sir. E plus
E
VC1.
plus E minus Vf.
VF.
That gives me 2 times
Twice.
E minus Vf. That is the voltage at point A. Now, if voltage at point A, obviously this is going to be a positive voltage. Voltage at point A is 2E minus Vf. So, what will be the status of this diode now, D1? Whether it will be forward biased or reverse biased? D1 is
D1.
reverse bias. Excellent. Why? Because cathode is at a higher potential than anode. So I can
Anode.
simply ignore this as if it is not there. All right. Is that fine? ठीक है ना? Now look at what is the condition
Yes.
across this D2. What will happen to D2? What is the voltage at the cathode of D2? What is the
2E
voltage?
minus Bf.
What is the voltage at cathode here? What is the voltage at cathode of D2? Remember again the same principle. When capacitor is not charged, it acts like a short circuit. So as if this is a short circuit, right? So what is the voltage
Yes,
at
sir.
the cathode of D2? It is 0 volts. Ground.
Zero.
Connected, no? Short circuit. ठीक है ना?
Yes, sir.
So what will happen to D2? Anode is at a higher potential. Cathode is at a lower potential, that is 0. So D2 is
Forward biased.
forward biased. Now if D2 is forward biased, again it means that I am having a path and Of course, there is a capacitor here which is not charged, but now what will happen? This capacitor will start getting charged. What will it get charged to? What voltage will it get charged to? VC2.
2E minus VF.
Yes, VC2 will get charged to 2E minus V. But don't forget one interesting thing that is happening here. You are forgetting the forward voltage drop across the diode. Call this VF2. If you call this VF1, anyways, they are going to be same. So it is the capacitor voltage going to be VC 2E minus VF1 only?
No, 2E
Don't
minus
forget
VF1
yes,
minus
don't forget
V2.
the drop across this diode. So it's going to be
2V.
minus. Is that clear?
Yes, sir.
So what we have at the output voltage? What is the output voltage now? This is nothing but the output voltage. Capacitor voltage output is nothing but this is the output voltage. So what is the output voltage? Output voltage is 2 times E minus VF. All right.
Yes, sir.
And most of the times, as compared to E, this VF is very small. Okay. Just like in case of the power transformer, or let us say the power supply, if your input voltage peak to peak values are in the range of like plus 10 volts, minus 10 volts, and so on. So as compared to these values, 0.7 volts is very, very small. So I can approximately say that this is 2 times E if I ignore this VF. What we have got is, yes, a voltage doubler. Are you getting this? Have you understood the operation? Guys?
Yes, sir. Sir, you were not audible.
Okay, I was asking, does anyone have any doubt about the operation?
So, sir, this voltage doubler is only for the positive half cycle.
Yes, of course.
Yes, sir.
But it doesn't matter. If you want a negative voltage, what can you do? Just reverse the load.
Yes, sir, Lord.
That's it. It doesn't matter.
Yes, sir.
Okay.
Yes, sir.
All right. But life is not that simple. This guy is always going to have its own problems. So it might be possible for you to say, okay, fine, with such a kind of circuit, if I'm having plus 10, minus 10 volts or 10, 0, 10 kind of a transformer, I can have a peak value of the input waveform. I can generate nearly a DC value of 20 volts. This is what you might come to the conclusion, no? Obviously, this is what we are being looking at.
Yes.
Okay? But the problem here is that since it is a capacitive storage, we are storing the energy in the capacitor, and the capacitor storage, we already know that the capacitor will always discharge through the load.
Yes, sir.
Whenever this diode is off, this capacitor C2 will discharge through the load. Okay, and that is the reason why we may have some kind of a ripple at the output. This is what I was talking about. So this is what will happen when C2 partially discharges.
Yes, sir.
So you have a ripple here. You will not have a clean DC waveform, but you may have a ripple. And the higher the load current, the bigger is going to be the ripple. Okay. So capacitor C2 takes a very important should take a very important consideration. So C2 supplies load current IL when D2 is reverse biased. But what about C1? C1 supplies 2 times IL when D2 is forward biased. Look at the condition here. This capacitor C1, okay, it supplies, first of all, it supplies charging current to this guy, as well as it supplies load current when this diode is forward biased. So naturally the capacity of C1 is twice that of C2. So while selecting the capacitor, we have to make sure that the value of capacitor is twice that of C2. Okay. Now how to find out the capacitor value? C2 is given as IL into T divided by delta VC. Where do I get this equation from? Guys, we have seen such a kind of equation. Again, concept, voltage across a capacitor is 1 by C integral IDT. Guys, are you there with me?
Yes.
Yes, sir.
Yes, sir.
So I'm assuming that the capacitor is now discharged with a constant current source. So if that happens, VC is 1 by C in I into the T. This is where this equation is the picture. So C can be found as I into T by VC. So this is the equation that I am using. You should know how this equation has been derived, or it has been applied. Okay, and as per our logic, your C1 will be twice that of C2. These are going to be the design requirements. Of course, you cannot eliminate the ripple completely. Please remember this. Okay, so that is what we have for today. I think we have already run out of time. So tomorrow we will take up an example for the voltage voltage doubler, and then we will go on for voltage multiplier or multi-stage voltage multipliers. All right. So we'll stop here for today. Yes. Any doubts? Any questions?
No, sir.
All right. So we stop here for today.
Thank you, sir.
Okay. Thank you.
Thank